Last class we studied about the work done by a constant force, okay, and the work energy theorem for a constant force. So constant force means a fixed force. So the work done by a constant force, the formula is W equal to Fd cos theta, where F is the fixed force, constant force. Now our topic is work done by a variable force. For variable force means the force is changing. Okay, so how will you calculate this work done by a variable force? For the constant force we have one formula, W equal to Fd cos theta. That formula is not suitable in this case. Okay. So, to find out the work done by a variable force, we should draw a graph. Okay, that graph consisting of force on the y-axis and the displacement on the x-axis. So, the force is a variable one. So, the nature of graph is not a straight line, it is a curved one. Okay. So, this represents that at every point the force is changing. Clear? At every point the force is changing with respect to the displacement. So, we can say that force is a function of displacement. That we can write it as f of x. Okay, force is a function of displacement. It is represented as f of x. So, look at this graph. So here, suppose an object, its initial position is xi. So from the initial position, the object moves through a distance and reaches the point xf. So this is the displacement of the object. Okay, this is the displacement of the object. So that is, this distance is moved by the object under a force F. So, you want to calculate the work done by the object when it moves from xi to xf under this variable force. Clear? For that, you should divide this displacement into a large number of small equal displacements delta x. Okay, this is represented as delta x. So, to calculate the work done by the object, you should divide the displacement into small displacements, into a large number of small equal displacements delta x or dx. We can say that dx or delta x. Okay. So, consider you consider one such displacement dx. Okay, here I noted the small displacement as dx. So, you consider one such displacement dx, and here you assume the force to be a constant one. So, what is the work done for this small displacement dx? That we noted as small work done dw. Okay. Small work done dw equal to force. Okay, force is assumed to be constant. Force into this distance f into dx. Understand? The small work done for the displacement dx is f into dx. So that f is the, we are considering this dx in the form of a rectangle, isn't it? That is the ABCD. So this rectangle is represented as dx. So this f is the length of this rectangle and dx is the breadth of this rectangle. So what is this length into b? That is length into breadth. That is the area of this rectangle. So we can write f into dx equal to area of the rectangle. Okay, area of the rectangle ABCD. Clear? Area of the rectangle ABCD. that is under this small displacement dx, under this small curve. Okay, so this area of the rectangle ABCD is under this small curve dx. Clear? Then, so to get the total work done, that means here number of dx is there, number of small equal displacement dx is there. So the dw is for the one such displacement dx. So to calculate the total work done from xi to xf, you should add all the dw of all the dx, isn't it? You should add here also dx. So one dw is here, and here also dx, then dw here, and dw etc. So to get the total work done from xi to xf, you should add all the dw. Clear? So we can write the total work done w. Okay, total work done w equal to, for adding you should take the summation. Okay, summation from where to where? Xi to xf. Okay, summation xi to xf, then this dw. Okay, you should add the dw from xi to xf, then we get the total work done. So that is equal to summation xi to xf. Okay, what is dw here? F dx. Understand? F dx. So this summation xi to xf, f dx is equal to the area of all the rectangles, sum of the area of all the rectangle. So here dw equal to, okay, we are considering one small displacement dx. So what is dw for that dx? It is equal to area of this rectangle ABCD. So when you take the summation of all dw, it is equal to the area of all the sum of the area of all the rectangles. Clear? So we can write total work done equal to sum of area of all the, okay, sum of area of all rectangles. Understand? Sum of area of all rectangles. So small work done dw equal to area of one rectangle. Then total work done equal to sum of area of all rectangles. Understand? Then if you take the delta x to be 0, okay, you take delta x tends to 0. So this delta x tends to 0 means, or how can you draw here if the delta x, so this is the delta x, isn't it? And if this delta x is 0, it is assumed to be 0, then we can take the delta x like this or dx like this. Okay, dx or delta x. Okay, so here we are noting the dx, so we can write the dx. So this dx tends to 0, then we will get the dx like this. That is a small line, isn't it? So the number of this rectangles tends to be 0. If delta x tends to 0, so we get number of infinite rectangles. So what is the total work done relating? That means total work done when we are considering this infinite number of rectangles. So we can take the integration. In this case, we can take the integration to take the sum. So here we apply the limit, isn't it? In the above equation, we can apply the limit. Limit dx tends to 0, sigma xi to xf, f dx, isn't it? F dx. Then we can take the integration. Okay, when you are applying the limit, then we get a number of infinite rectangles. So to take the, or to find out the total work done, we should take the integration. Integral xi to xf, okay, f dx. So integration means when you join the small things, we get a large one, isn't it? That means addition. When you adding the small things, we get a sum of that one. Okay, that is the integration. Integrating, we can take the sum. We can add the small things, then we will get a large one. Okay, that is integral xi to x of f dx. So this work done xi to x of f dx is equal to what? It is equal to the area under this curve. So here dw equal to area under this small curve dx. So total work done integral xi to x of f dx means area under this whole curve, isn't it? So we get the work done equal to area under this force displacement curve. So we can write work done by the variable force equal to area under the force displacement curve. So you can find out the total work done for a variable force. How can you find out the total work done under a variable force? It is equal to the area under the force displacement curve. Clear? So total work done by a constant force, we have one formula, W equal to Fd cos theta. But total work done for a variable force, we can calculate it from a graph. It is equal to the area under the force displacement curve. Clear? Next topic, work energy theorem for a variable force. Same as the work energy theorem for a constant force, here also the statement is work done equal to change in energy. So you want to prove this one. Okay, for a variable force, you want to prove that work done equal to change in energy. So when you apply a variable force, the body moves. So the energy possessed by the body is kinetic energy. So we can write kinetic energy K equal to half mv square. Then we can differentiate both sides, that is kinetic energy changing with the time. So we can write dk by dt, kinetic energy changes with the time, dk by dt, that is equal to, so this is also d by dt of half mv square. Okay, then we can differentiate this d by dt of half mv square. So that is equal to half into m, okay, that is constant, that is m. Then d by dt of v square, that is equal to 2v into dv by dt. So that is differentiation d by dx of x raised to n, that is equal to n into x raised to n minus 1. Similarly, d by dt of v square, that is equal to 2v raised to 2 minus 1 into, once again differentiate this one, dv by dt. Okay, so here 2 and 2 we can cancel. Then dk by dt, okay, dk by dt equal to mv dv by dt. So what is dv by dt? That is equal to acceleration. So we can write mva. So m into a, that is equal to force. So we can write dk by dt, that is equal to m into a f into v. So what is v? V equal to dx by dt. So f into, okay, in terms of the displacement, f into dx by dt. So when you are applying a variable force, the object moves from the initial position xi to x up. So its kinetic energy is also changing from initial kinetic energy ki to kf. Okay, so here we can cancel this dt. So we can write the dk. Okay, dk equal to f dx. Isn't it? So in this case, once again, when you are applying a variable force, the object moves from initial position xi to x up. So its kinetic energy is also changing from initial kinetic energy ki to kf. So we can apply the integration here. That is integral ki to kf dk equal to integral xi to xf f dx. So we can apply the limit, that is integral ki to kf dk. So we can write within the limit k, that is ki to kf, within the, that means we can write like this, that is equal to in within the limit, okay, that is ki to kf equal to integral xi to xf f dx. So we can apply the upper limit and lower limit, that is equal to kf minus ki equal to, what is this, xi to xf f dx, that is equal to the work done. So that is work done equal to change in kinetic energy. So we proved the work energy theorem for a variable force. When you are applying the variable force, we get work done equal to change in kinetic energy. So this is true for both the constant force and for the variable force.